First thing, before we can talk about the general addition rule, we need to talk about this idea of mutually exclusive, or what's also known as two disjoint events. So there's two different terms that mean the same thing. So mutually exclusive events are two events that cannot occur at the same time. So if I were to roll a die, two events that would be mutually exclusive would be rolling an even number and rolling an odd number. If I look at those two events, can I ever get a number that is both even and odd at the same time? No. That's what we mean with mutually exclusive. So when you have two events, we're looking at, can any one single outcome satisfy both of those events? Okay? And if the answer is no, it cannot satisfy both, then they're mutually exclusive events. They have nothing in common, no overlap. But if we can think of an example where the two would overlap, then they're not mutually exclusive. The other thing to note here, these will also be called disjoint events. So disjoint and mutually exclusive mean the same thing. You need to know both because they'll be used interchangeably throughout the book. And then on quizzes and tests, same thing. Sometimes I might say mutually exclusive, sometimes I might say disjoint. So, when we look at the events, a way to think of this pictorially, if we look at the left Venn diagram here, A and B are mutually exclusive. Event A over here has a collection of outcomes within the circle. Event B has a collection of outcomes within its circle. Now, at any point, do A and B overlap? No, which means there's no one single outcome that can be in both A and B at the same time. In our second problem, or second example here, we have event A and event B here. Now they do have some overlap. So right here, what we're saying is there are some outcomes. There's at least one outcome within this sample space that would satisfy both event A and event B. So rolling a die, that might be, like event A might be rolling an even number. And event B might be rolling a number greater than 2. So if I have one event is rolling an even, what are my options? 2, 4, and 6, right? So 2, 4, and 6 would be my outcomes that are even. Rolling a number greater than 2, what are my options? 3, 4, 5, 6, right? So where would the overlap occur there? 4 and 6, right? Both 4 and 6 are even, and they're greater than 2, right? So those would be not mutually exclusive events because there is overlap. There are two outcomes that satisfy both conditions, okay? So when we say mutually exclusive, you're looking for outcomes, or you're saying that the two events have nothing in common whatsoever. There are no outcomes that can happen for both. So let's go through a couple examples here. So your job is to determine if the events are mutually exclusive or not, or if they're disjoint or not. So if I roll a die, would rolling a 3 on a die and rolling a 5 on a die be mutually exclusive? So what you have to ask yourself is when you roll one time, can you roll a 3 that is also a 5? No. Either you roll a 3 or you roll a 5. There's no number that's both. Okay? So these would be mutually exclusive. How about randomly selecting a male college student and randomly selecting a math major? So if you're on a college campus, you're going to randomly select a male college student, randomly select a math major. So can you select a male college student that is also a math major? Yeah, more than likely, there's at least one male that's also a math major. Okay? So those would not be mutually exclusive. Randomly selecting a blood donor of type A positive and randomly selecting a female blood donor. So are they mutually exclusive or not? No. If you selected a person, they could both be a positive and be female. So they are not mutually exclusive. So first one, definitely mutually exclusive. The next two are not disjoint, because there are outcomes that would satisfy both of those conditions. Now the key thing here is always remember, you have two different statements, rolling a 3 and rolling a 5. But that is actually looking at one overall outcome. So I'm rolling the die once, can I get something that's both? Okay, so it's not like it's two separate occurrences where I roll a 3 and then the next time I roll a 5. That's not what we're asking. It's saying on one churn, can we get both of these things satisfied? We okay with that? Okay. So let's talk about the general addition rule then. So the general addition rule is used when we want the probability that one of two events occur. So basically, what's the probability that either event A or event B? So the key word here, what you'd be looking for in the problem, if they use the word or to describe the two events, you are going to be using this addition rule to calculate your overall probability. What's the probability that this or this happens? So that's something you definitely want to write down or highlight in your notes. The word or is your key term. The other thing, this is for one single event. It's important that you guys realize that even though it's two different events that we're looking at that occurring in one single outcome. Okay, so we're only performing one trial, which means we're only going to be considering one outcome. So what the addition rule says, looks like this in notation. Get the notation copied down and then we'll talk about what the notation actually says here. Knowing what notation means is going to be extremely important for you guys. You need to understand what the different symbols mean and how to put them together. You have to know this formula and know how to use it. So in the formula here, the first part, this probability of A, U, B, this little U symbol, what it usually, or actually stands for is the union. We're thinking of event A and event B as being two sets, two overall sets of outcomes. So we look at the union. That's the or part of our statement. So this first part is saying, what's the probability that event A or event B occurs? So anytime you see that little U being utilized, that is denoting the word or. Then we have probability of A plus probability of B. That's just your standard probability notation. Minus the probability, and now we have this A and this little upside down U symbol B. This upside down U is the intersection of the two events. What it literally translates to in English is the word and. So the last part of that statement is the probability that A and B occur at the same time. So one of the things you might want to highlight there, this symbol in English essentially means and.
Is the first one the and also? Like the normal U? Yeah.
This means or.
Or? Okay.
Okay? So the U means or. If we flip it upside down, it becomes an and. Okay? So this is the probability that either A or B occurs. The last part says the probability that A and B both occur. So those are the ones where they have to happen at the same time. Okay? Now, think about this statement here. If I want the probability that A or B happens, we take the probability of A plus the probability of B. That makes sense, or should be pretty intuitive, right? Why do we have to subtract out the probability that both are occurring? Because we're double counting. Think about what we're doing here. If we look at the picture, when I take the probability of A, that's all of these outcomes here on circle A, right? So I'm going to include all of these in the probability of A. Everyone okay with that? Now when I look at the probability of B, that means I'm going to add in all of these outcomes to my formula. So I'm going to add in all of these values. Well, so notice if I count every outcome in A plus every outcome in B, what's happened where they overlap? I'm counting those twice. So what I have to do, since I have two sets of those values, since I have these values counted twice, I need to take one of those sets out. So because I'm double counting this area, I need to subtract one of those pieces out. That's why we have that whole subtract the probability of A and B, to get rid of any double counting. Now, notice, if I look at my two events here, event A and event B, are they disjoint? No, they're not. There's overlap, right? So think about this. If I had two events that were mutually exclusive, so if events A and event B were mutually exclusive, how would that change my formula here? Or would it change it at all? Why would there be nothing to subtract?
There's no overlap.
Because there would be no overlap. If A and B are disjoint, that means they have no outcomes in common. So if I were to look at that in a picture here, that would mean I'd have event A here, I'd have event B somewhere over here. There's no overlap. So if I take all of my outcomes in A plus all of my outcomes in B, I haven't double counted anything because none of my outcomes happened for both. So when we're looking at this formula here, if we have mutually exclusive events, that last probability is always going to be 0. There's never going to be any outcomes that satisfy both A and B at the same time. So when you're using this rule, there are times where you can take A plus B and be done. But that only happens if you can say that events A and B are disjoint. If they have any outcomes in common, you have to subtract out what they have in common so that you're not double counting.
So would the first part of the equation always be like 100 then, or whatever, or 1?
What do you
And
mean?
a mutual exclusive? Like, wouldn't it be like, there's a 100% chance you'll get A or B?
Well, not necessarily, because if we think of so this picture, what we're denoting, we have event A, we have event B. This box around here, this is our sample space.
Okay.
So there might be 100 different outcomes in the total sample space. Event A might only account for maybe 20 of the outcomes, and event B might account for 10 of the outcomes. So A and B don't encompass the entire sample space necessarily, because there are other outcomes that don't satisfy either condition. So then, in this case, we just have to think about the individual probabilities on their own. Okay? All right. So, let's get some practice working the formula here. So we want to find the probability of selecting a queen or a king from a standard deck of cards. So one of the things I hope you guys have been doing, if you're not familiar with the deck of cards, you need to be getting yourself familiarized with those. Okay, you need to know how many numbers are in each suit, how many total suits there are, how many face cards, things of that nature. Okay, so all those things are going to come into play with a lot of the probabilities we're going to be dealing with. So the probability of selecting a queen or a king from a deck. So what I want you guys to do with these problems is I want you to write everything out. Write out the notation so you get used to seeing what it looks like in the equation and what you're plugging in where. So if I'm looking at this problem here, if I were to write this out in notation, I want the probability of selecting a queen or a king. So the probability of selecting a queen or a king. So in notation, that would be, you can just denote Q for queen, K for king, and then the union symbol, the U.
So that it will always be a union symbol. You don't like add, like on the, when it says and, you don't add those or anything.
Well, if it's a and problem, probability of drawing a queen and a king, that's going to be a completely different formula that we use.
Okay.
So when it's or, it's always going to be you to start with.
What about for like the second part?
The second part will always be and.
Okay. It's always just the simple.
Yep. Okay. So the probability that Q or K happens. Okay. Now, based on our formula, that means I'm going to take the probability of a queen plus the probability of a king minus the probability of drawing a queen and a king. Okay? So, if I want to calculate my probability here, what is the probability of drawing a queen from a standard deck of cards?
4 out of 42.
4 out of 52. 4 queens out of 52 total cards. So we'd have a 4 out of 52 plus the probability of a king, 4 out of 52, minus, if I draw one single card, what's the probability that it's both a queen and a king?
0.
0. These are mutually exclusive events, right? So since they are disjoint, we could actually forget about this last piece altogether. There's no way to draw a queen and a king on the same draw. So really all we have to do is take the probability of queen plus the probability of king. Oops, thought I had my answer up there. So 4 out of 52 plus 4 out of 52. Everyone okay with that? So we have that. The 0 is denoting that it's disjoint. There is no queen and king in the deck. So 8 out of 52, or in decimal form, that would be 0.15. Again, when you report your probabilities, you can do it as fraction form or in decimal form. Doesn't matter there.
Should we reduce?
I would reduce, yes. So if you're going to leave it in fraction form, reduce the fraction. Otherwise, if you go to decimal, just give me the decimal. Okay? Now let's take a look at the second one here. So in the second problem, find the probability of selecting a queen or a club from a standard deck. So in notation, the probability of drawing a queen or a club would be equal to the probability of drawing a queen plus the probability of drawing a club minus the probability of drawing a queen that's also a club. So if we look at our expression here, the probability of drawing a queen is still 4 out of 52. The probability of drawing a club, there are 13 clubs out of 52. In this case now, queen and club are not mutually exclusive because there is a queen of clubs. So we need to subtract out the 1 queen of clubs out of 52 because we would have double counted it. We counted the queen of clubs once here in the 4, and we counted the queen of clubs once here in the 13. So we need to subtract one of them out to get our overall answer. So you get a 16 out of 52, which would reduce, or in decimal form, 0.31. Okay. So one of the things I want you guys doing in your homework, I do want to see this. When you're calculating the probability, I want to see the formula you're using. Okay, it gets you guys used to seeing it. It gets you guys used to figuring out what you plug in where, and then solving from there. Okay, but I want to see that. Any questions on that general addition rule? So anytime you have the probability of one thing or another happening, it's always that general addition rule. So probability of one plus the probability of the other minus any overlap that they might have. Okay there? All right. Then, the next piece that we need to talk about, there are times where it might be beneficial for us to know what the probability of one but not the other event that would occur. So the probability that event A but not event B would happen. So when we look at that example, what's the probability that A but not B happens? what we're going to essentially do is take the probability that A happens, but we need to subtract out the probability that both occur at the same time. So if they're not disjoint events, that means there are some outcomes that work for both A and B. Well, if we only want outcomes that work specifically for A, but they don't want outcomes that work for B, we want the outcomes in A minus any outcomes that also work for B. So this would look something like this. So what's the probability of event A but not B? So probability of all the outcomes in A minus the probability of any outcomes that happen for both A and B. We don't want B involved at all. This idea comes into play pretty big with our Venn diagrams. So we're going to talk about the Venn diagrams here in a little bit. This is going to be a very important part of that. Okay, so if we put this into an example here, we want the probability, so drawing from a standard deck of cards, probability of drawing a king but not a heart. Okay, so the probability we draw a king but not a heart. So if we're looking at our formula here, that says to find the formula or find the probability of drawing a king minus the probability of drawing a king that is also a heart. So how many kings are in the deck? 4. So I'd have 4 out of 52. Minus how many kings also are also hearts? 1. So we get an overall probability of 3 over 52, which we could reduce down or put in a decimal form. Okay with that? Okay. All right. So, Venn diagrams. Venn diagrams are a way for us to organize information from a problem in a way that's more visual. So we can actually create a diagram that's going to give us a visual of our different probabilities, which will make it easier to calculate exactly what we're looking for within the actual problem. So what's going to happen is they'll give you situations like this. Police report that 78% of drivers stopped on suspicion of drunk driving are given a breath test. 36% are given a blood test, and 22% are actually given both tests. We want the probability that a randomly selected DWI suspect is given, first, a test in general, second, a blood test or a breath test, but not both, and then neither test. Okay? Now, if all we're doing is looking at this in terms of words, this can be very confusing and it can be tough to figure out or visualize exactly what we're working with. Okay? So, what we need to do, or what we can do, I should say, is create a Venn diagram. You guys have all seen Venn diagrams before, yes? Okay, so that's where you have the two circles, they overlap, and you can put any outcomes where they need to go, right? So kind of like what we're doing with the mutually exclusive events, things like that. So the first thing you need to do is create your Venn diagram. So create your sample space, which is going to be denoted with a big rectangle on the outside, and then put your two events inside. So you have event A and event B. So in this particular case, event A is going to denote the breath test, and event B is going to be the blood test. So basically, create your two events, show the overlap, and now what we're going to do is we're going to start figuring out how this is going to look here. Okay? So 78% of all drivers stopped, get a breath test, 36% get a blood test, 22% get both tests. Okay? So when we go to fill in our Venn diagram here, we know that within event A, so the breath test, this whole circle has to account for 78%. So within that circle, we have 78% of our outcomes. Within circle B, we have 36% of all of our outcomes. And 22% of our outcomes are where the overlap between A and B occurred. So when we go to fill this out, we want to start with the overlap. We're going to work our way from the center out. Okay? So 22% goes in the overlap. There are 22% of drivers who get both a blood and a breath test. Everyone okay with that idea so far? So that's just coming straight from the problem here. Now here's where people make their biggest mistake. What happens is they say that 78% get a breath test. So what happens is people put the 22% in the middle, and then they put 78% in for event A. But if I do that, what's happening is I'm saying that I have 78% here, 22% here. Well, that's already 100% of all of my values, which would leave me nothing for anything else. But we know that's not true, right? So when we say that 78% of all drivers get a breath test, that means the entire circle A has 78%. But we've already taken 22% in the overlap. So what we're actually trying to fill in here is how many drivers, or what percent of drivers, get a breath test, but not a blood test. So if I want the probability that they get a breath test, but not a blood test, what do I have to do? I have to take my 78 minus the 22. So we're going to subtract the 22% that works for B out of the 78. So that's where I'm going to get 56%. So 56% of my drivers get just a breath test. Same thing has to happen for the blood test. There's 36% that get a blood test, but 22% of those are also given a breath test. So I want the number or the percentage of drivers that only get a blood test. So how am I going to do that? Subtract again. So 36 minus 22 gives us a 14% chance. So there's 14% of drivers get just a blood test and nothing else. Okay? Now, we have event A, event B, and their overlap all accounted for. What's the only thing we haven't accounted for? The overall sample space. So we have here the probability that they get a test, but does this add up to 100% if I take 56 plus 22 plus 14? What does that add up to? 92%, right? So 92% either get a breath test alone, a blood test alone, or both, which means how many people, or what percent of people would not get any test? 8%. So one of the last things you need to fill in then is what's remaining for neither event occurring. Okay? So the first step on a problem like this would be to set up our Venn diagram. So start in the center and work your way out. So put the part where they both are occurring, find each individual piece, and then find the part where neither is occurring to find that sample space area. Now, this becomes a little bit easier to solve the questions that we're asking here. If we want the probability that they're given a test, it doesn't matter which one, it could be both, we just want to know what's the probability that they get a test. So how would we do that? Yeah, add up the insides, right? Take the 56 plus the 22 plus the 14, which would give us that would give us a 92% chance, right? So 92% of DWI suspects are given some form of test, whether it's a blood test, breath test, or both. I could have also used my complement rule. Since I know 8% of people don't get any sort of test at all, that means 92% have to be getting some type of test. Okay, so the complement rule would work here as well. So there's the first one. How about the probability that they get a blood test or a breath test, but not both? So only a blood test or only a breath test, but not both. So if I want that probability, what am I going to do here? So what would I do? Blood test or breath test, but not both. So add event A and event B, well, that would be 78 plus 36.
The values after you subtract the 22.
Okay, so we want just breath test, which would be only the 56%, right? So I take the 56% for A plus the 14% for B. So if I do that, what's the probability that they get one or the other but not both? 70%. And then the last one, what's the probability that they get neither test? 8%, which was already calculated for us. Okay, so when you get situations like this where they're giving you some information about a couple different events, a Venn diagram is usually the best place to go. It's very easy to set up, and then you have every probability or percentage that you could possibly need. All you have to do is figure out how to put them together. Okay with that? Okay. Two-way tables. So another way we evaluate probabilities is based on information in what we call two-way tables. Two-way tables look a lot like contingency tables, stuff we talked about way back in chapter 1. Okay. So in a two-way table, we're evaluating two different variables. So in this case, we happen to be looking at the IQs of a certain group of people, so high IQ versus normal IQ. And what they're looking at is the presence or non-presence of a specific gene in those particular people. So two different variables that we're analyzing, and they give us the information based on what they found. So 33 of the high IQ people had the gene present. 39 with the normal IQ had the gene present, and so on. So it's read just like we would have read our contingency tables before. What's going to happen now is they're just going to be asking us how to find different probabilities based on the information in the table. So for instance, if we wanted to find the probability that a child has a high IQ, what would I do here? Take the 52 total high IQ kids and divide by the total number of kids in the study. So we just take 52 out of 102, which you can either reduce down as a fraction or give the decimal, which would be about 50.1%. So some of the times, all you need to do is take the totals, calculate the probabilities. Probability of high IQ, 52 out of 102. Okay. What about the probability that a child has the gene present? (72 out of 102). So 72 of the kids had the gene present out of the 102 total kids. So 72 out of 102, which could be reduced, or decimal version 0.706. Okay, so some of the initial ones, pretty straightforward. What if we want the probability that a child has the gene present or has a high IQ? So what's the key word in this statement? Or. As soon as we see the or, we're looking at one event or the other. What rule are we using? The addition rule. Okay? So we're looking at the probability that the child has the gene present or has a high IQ. So if I write out my formula, the probability that they have the gene or a high IQ. What does our addition rule say to do? Probability of the gene in this case, yeah, so probability of the first event plus
Wait, what's the other option?
high IQ.
Plus.
So probability of gene plus probability of high IQ minus the probability that they have both. So that they have the gene present and also have a high IQ. So if we're looking at this in terms of our two-way table, what was the probability that they had the gene? 72 out of 102. What was the probability of having a high IQ? 52 out of 102. What's the probability that they have both the gene and a high IQ? 33 out of 102. Okay, so 33 of the kids had both the gene and the high IQ. So when we go to calculate this out, we have our 72 over 102 plus 52 over 102 minus 33 over 102. So again, you can combine that into a fraction or decimal version 0.892. So if you selected a kid at random, there'd be an 89% chance that they would have the gene or a high IQ. Okay with that?
Yeah.
Okay. And that's it.
Yellow.